We are taking a bottom-top approach. We have covered a lot of SLAM components already in the MVG lectures, and the linear algebra was also briefly covered in the initial lectures. Now, in today's class, the remaining prerequisites will be covered, and 3D, visual odometry part will be finished component-wise. So tomorrow, and we'll also be covering loop closure. We'll be covering bag of words, which we'll be using tomorrow. That's also a crucial component of SLAM. And tomorrow we will jump right into SLAM. We will start with SLAM front end, SLAM backend, and then you'll be able to connect all the dots. So even in SLAM front end, we'll be only looking at it component wise. SLAM backend, same, and then we'll visualize the whole thing. We'll visualize how, let's say PNP connects in the SLAM pipeline, or let's say least squares optimization. Where does that come in? So you'll have to be patient till that lecture, till that part. Tomorrow, probably halfway through, we'll reach there. Okay. So today I'll start with least squares optimization, and I'm starting from the very basics, but I'll be going quite fast. If you have any doubts, do stop me. These concepts have been briefly covered by Ayappa already. So yeah. Okay. Yeah. Okay. Now, so whatever in most of your SLAM problem or computer vision problem, whatever the problem is, at the end of the day, you want to minimize an objective function. You want to minimize a loss function, an objective function, whatever you call it. So the question is, how do we approach towards that? What are the various approaches towards that? And if the objective function is linear in nature, what do we apply? If it's non-linear in nature, what do we apply? So we usually pose it as a least squares problem. That is what we'll be looking at today. Okay, so let us start from the bare basics, linear algebra. And yeah, a couple of notes here. One is we will be only considering overdetermined systems. Why is that so? Because in most cases, that is how it's going to be. For example, let's say in F matrix computation, it's not like the bare minimum number of points we needed was 8, but it's not like you only would have 8 correspondences. Let's say if you apply surf or SIFT, right? You have lots of them, and that is how it's going to be in whatever example it is. You always have more number of equations. You want to, you want to estimate the best solution from these huge number of equations. Secondly, we'll only be considering full rank matrices throughout the entirety of this lecture. That is how it's going to be in usually also. You'll have noise, so it will end up being a full rank matrix. And today and tomorrow we'll mostly be dealing from a practical point of view. So yeah, if you want to go deep into theory, there are lots of links here. You can definitely do that, right? And also, yeah, there are definitely special cases like low rank. When we had to enforce low rank in F matrix computation, we used a special technique. That sort of things won't be covered here. And also say you do not even know the rank of a system. How do you minimize such a system? For this lecture, in today's time constraints, we won't be covering that. Yeah, so it is full rank and overdetermined system assumed throughout this lecture. Okay, so let us look at this crucial case considering only linear algebra. You can take a few seconds to recollect. R is equal to n. Rank is your m is greater than n. That means number of rows is greater than number of columns. Now you are asking what is my solution? Okay, so how can you interpret this? You have a full rank matrix. Let's say over here, let's consider, for example, you have 7 rows and 5 columns. Now, if your vector B lies in the column space of A, which would be, let's say, your x is x1, x2, x3, x4, x5. Yeah, and your each column vector would be of size 7 vector. So it will be x1 into first vector plus x2 into second vector and so on. This will definitely span some space, but it will not span the entire all 7 space, right? So it will span some. It is like the analogy you can think of is it will span a 2D space in a 3D space. So, but your B need not necessarily be on this particular line, on this particular plane. So you either have zero solution if it is not lying on this plane, or if it lies on this plane, you have one solution. So that is sort of your whole linear algebra for overdetermined system in this particular scenario. R is equal to n less than m. Okay. Now have written down the explanation here, but if you don't understand this, go back and revisit linear algebra. Okay. So, but in reality, this never happens, right? Like, just think about it. It's a 3D space, and your B vector can be lying anywhere. So it's very unlikely, let's say in a practical situation, for it to exactly lie on a 2D plane. So in such situations, what do we want to do? We just say, okay, maybe I cannot, maybe AX, the linear combination of column space or linear combination of columns of A might not exactly reach B, but what I'll do is I'll rather minimize the distance between AX and B. Yeah. So least squares. There are again two perspectives to this. Linear algebra perspective. The second is calculus perspective. I'll be covering linear algebra perspective at a high level. Calculus, I'll go into detail. So linear algebra, from the point of view of, let's say, geometrically, by looking at that figure on the right, that's from Gilbert-Stan's lecture. I will later on replace it with Tick's code or something. So over here, you have a B vector which is not lying on A. Or in our case, it would be a B vector is not lying in the column space of A. Now, the closest to a point to a plane is, you just drop a perpendicular from a point to a plane, and then over here, the closest this B could reach your A would be over here. It's a two-dimensional thing. That's why. But in our case, it would be column space. I mean, whatever this vector that you see would be a 2D plane or 3D plane, depends. Yeah. So the closest that I could get would be the projection of B on my column space. That would be your answer. And if you try to use geometry and take dot product of this with this and then equate it to 0, this should be perpendicular to this line, and then we want x here. XA is perpendicular to P minus P. B minus XA. P is nothing but XA. You end up with a solution. You will end up with this particular solution, A transpose A, X is equal to A transpose B. You can put that on paper and see that for yourself. Now, to that is like you can take it as a practice problem. Calculus perspective, I'll now cover in detail. Okay. So we said we wanted to minimize AX minus B, the norm of AX minus B. And when we say the norm, we usually mean L2 norm. You know what L2 norm is? Root over A1 minus B1 square plus A2 minus B2 square, whatever. Now you know that the norm ax minus b is not differentiable. I mean, you can't differentiate it, and you cannot say anything about the convexity. So what we do rather is we square this norm for the sake of convenience. I mean, you cannot just square like it. You also have to ensure that the whatever you have squared least, I mean, minimizing the norm and minimizing the least squared norm are equivalent problems. If you want to know how those two are equivalent problems, you can go through this. But they are equivalent problems. That is why we square it and say I want to minimize this. Now this becomes differentiable. We had a problem before. We were not able to differentiate a norm of x minus b. Now we squared it, and now we are good to go. We have squared it up, expanded it, and now it's differentiable. We can differentiate it easily. Okay. Now I was saying, so let's cover the contents of this lecture. I'll start with linear least squares. I have already explained the linear algebra perspective, and then I've explained why we do not use that as it is in practical situations. We pose it as a least squares, and then I'll come to the solution. There are multiple solutions for linear least squares, and then I'll talk about non-linear least squares. For example, you have a neural network, deep learning. Now it's a crazy function, right? It's a composite function. It's a function of function of function of function. That's what a neural network is. So over there you can't. It's not a linear function, so you cannot apply these methods. Over there, in most situations, we apply gradient descent, but in other situations, we apply more complex methods. And then I'll also be covering non-linear weighted least squares. This is like after we cover this, we'll jump right into Slam backend tomorrow. I mean, from here, from what next, we'll go directly into Slam backend. So, and the math will pick up fast from here to here, from Ax is equal to B to just so your equation, the final equation that you end up would be this. So, do pay attention, and then that will have a direct application in Slam backend. I think that is good enough motivation for you guys. Okay. Okay, so I said in the first half of the lecture we'll be covering linear least squares, right? But over here this looks like a non-linear function. Why am I x transpose a transpose a x? This particular equation looks like a non-linear function. Why am I calling it linear least squares? Can anyone tell me? Are people able to follow? Okay, we have 17 people. Nice. If someone has joined late, I can repeat any parts. Do you want me to because it's important to understand from the starting. Okay. So the reason we call it linear here, so linear refers to this particular function ax minus b, and least squares refers to this squaring. So we are squaring a linear function and want to find the least value of it. We want to minimize it. That is why we are calling it a least squares function, least squares optimization. And over here ax minus b, the function f of x inside this norm, is a linear function. That is why it's a linear least squares. Is that clear? Okay, sure. I will repeat, but I'll go fast. Okay. Okay. I was saying, you want to, like, initially we were looking at the linear equation Ax is equal to B, and in most practical scenarios, in almost all practical scenarios, it would be a full rank matrix and an overdetermined system. In those situations, we want to know how we can find the solution X. That would be our whatever, let's say your F decomposition, or let's say SLAM backend also, you'll need these concepts. Wherever you see, you'll keep ending up with a linear system or a non-linear system. Basically, you want an X. You want to find what X is equal to. Tomorrow you'll see lots of cases of these sort of equations, because I'll be going through the entire SLAM system. You'll see how many places these things can appear. So we said it's a full rank matrix, so R is equal to n, and it's overdetermined system. Number of rows is greater than number of columns, so m is greater than n. And for this particular case, from linear algebra, you either have zero solution or one solution. It's one solution when B lies in the column space of A, but that is a bit unlikely to happen. So in such situations, we say, instead of trying to solve that Ax is equal to B, I'll just try to get my X as close as to B as possible. So for that, I said one linear algebra perspective of looking at it would be to project B onto your column space. And calculus perspective would be, firstly, this is not differentiable. So, like, you cannot say anything about this norm's convexity. So you square it. Least you square it. For this particular problem, least norm or least square norm are equivalent problems. So you square it, and then it becomes a square, I think. Yeah, fine. Yeah, it becomes a linear least squares. So I was asking, why is it linear? It is because Ax minus B is a linear function. Okay. Now we just expand it out. Ax minus B, norm square can be written as like A. Let's say you have some vector y. Norm of y square could be written as y transpose y. That is what we write here too. Ax minus B transpose into Ax minus B. If you multiply it out and expand it, you will get this equation. Are you comfortable with whatever I've covered so far? Have you at least understood why it's a, let's say, have you understood how we have reached at this equation, say? I mean, if you have a pen and paper, you can put it right now and see, convince yourself why you have reached here from here. Okay, I'll go forward then. Okay, fine. Now, this is my problem statement. I want to minimize this function. Now, the question is, how do I minimize it? What is my solution? Now, this equation that you see here, it's a quadratic equation. X transpose some matrix X minus some matrix into X plus some constant. This is a quadratic equation, and so you don't even need to have too much of optimization knowledge to understand this. In 11th and 12th, you have studied that if your double derivative of a quadratic function is positive, then it's a then if you equate the first derivative to 0, you'll get a minimum. So that double derivative of this would be A transpose A, and A transpose A is always positive definite. A transpose A, that the matrix M transpose M is always positive definite. So you equate gradient to 0, and then you say that is my solution. And I'm able to do this only because it's a convex problem. You cannot just take any function, not just take a derivative of it and say it's my solution. Only if it's a convex function. What is a convex function? You know that this is a convex function. I mean, yeah. So when it used to be like our curvature is positive here. So in such a scenario, what I would end up with would be a minima. Okay. So we take derivative of this and equate it to 0. We take gradient of this and equate it to 0. This B transpose B will disappear because it's a constant. Now 2 A transpose B will be as it is, and then X transpose A transpose A X, you take a derivative of this equation and equate it to 0. You'll end up with this. Basically X goes away, and then over here this is like you know, if you take a derivative of this, you'll get 2 over here. 2 into A transpose A into X is equal to 2 into A transpose B, and then you end up with this equation. I hope that is clear. It's just like, okay, let me not give a high school analogy. You'll have to read it as it is, because you need to know matrix calculus. When you take a derivative of this, you end up with 2 A transpose AX, and when you take a derivative of this, it will be minus 2 A transpose BX equated to 0. 2 gets cancelled. A transpose A is equal to A transpose B. These are called the normal equations of a least squares problem. That's the name. Okay, fine. Now you take A transpose A to the other side and you say that is your solution. X transpose is equal to A transpose A inverse A transpose into B. Just a second. Someone is telling me he's not able to join here. I just added. Yeah, till then you don't need to stare at my screen. You can go through that doc and put pencil on paper if you have not yet. Try to convince yourself how you have ended up from here to here, and then you can, like, there's so many things that you can do here. Put pen on paper. I'll just add him and come back. Okay. Has have you convinced? Has anyone of you convinced yourself how you reach from here to here? Give me a quick yes or no. Wait. You have to enable notifications. Yeah, awesome. Nice. Yeah, actually, like, please participate. That will make me more than energetic to present better. Okay, now that is called pseudo inverse. I hope. When did Adil say he'll start his class today?
Not today. He said he'll take it from tomorrow.
Oh, awesome then. Okay, fine. Then we can. We will probably go until 5 o'clock. Okay. Anyway. Yeah. Right. So we have looked at pseudo inverse. That is one way. I mean, analytically speaking, we just took a derivative of that, and then we ended up with this so-called uh, pseudo inverse matrix. So this would be my analytical solution. Now the other way would be to use QR. So what QR would do, it will save your computation. So here you have A transpose A whole inverse. Matrix multiplication is itself very computationally expensive, and then you have inverse on top of it. You have too many matrices. Compare that to QR. You directly end up with this equation: Rx is equal to Q transpose B. You can convince that by yourself. I mean, Q transpose Q would be I. You can substitute that here, and then you'll end up with this equation. Is Mithun here? Mithun is he here? Okay. Oh, okay, cool. Yeah, Mithun, if you have to add something anywhere, please interrupt me and feel free to if I'm going wrong or anything. Mithun is way more knowledgeable than me, and yeah. Anyway, let me go on. Okay, so I did make a comment here. If there's some question that I would like to. This is not like an official assignment, but if you'd like to answer these questions, you can. Or if something is not clear in my head, they also have commented. This will be like a nice note for all of us to use if all of us come forward and collaborate. Okay, using SVD, we have seen SVD multiple times in the MVG lectures, but that was mostly for AX is equal to B. Over there, we said my solution will decompose A into UDV transpose, and my solution is last vector in V corresponding to the least eigenvector. Over here, it is rather AX is equal to B. And yeah, for references, I have put book B, book C. At the starting part of the page, I have mentioned what book B, book C is. If you want to see the derivation or if you want to go deep, this is like you can go deep into it. This is the algorithm using SVD. You do an SVD and then define B dash as U transpose B, and then you define another vector Y, which is given by bi by di. M is greater than n, so you'll only have n yi's here, and then you apply your v into y. That will be your solution. I'm not going into too much detail here as well. You can take a look at the book C. Okay. Okay, what next? Nonlinear least squares.
Scott, I have a doubt. So everything that we did so far, we can just consider this as a linear regression problem, right? Because we have multiple data points and we have some features and we're trying to essentially find the line of best fit, and we are minimizing the distance between those points and that, right, with the least squares. So we can just use linear regression, right?
Yeah, so yeah, linear regression Yeah, it's nothing but linear least squares. I would say it's just a fancy name. Like mathematically speaking, it's the same. Mithun, if I'm missing something, you can add.
Yeah, they are the same. They are the same. Just two different statistics guys call it regression.
Yeah, yeah. Cool. So non-linear least squares. Okay, you can answer this. I have answered what was linear before. Now you tell me what is non-linear here. What is non-linear? Quick. Anyone?
F itself.
Yeah, f itself is non-linear. So we always look at the function f. Whenever we say linear or non-linear, we are talking about the function. We're not talking about this whole squared thing. So here f we consider the more complex case where f is non-linear, and again it's a we can rewrite this as f transpose into f. Half is just for the sake of clear writing later on. Okay, so far we have solved linear least squares analytically. We took a derivative and equated it to 0, and then we got pseudo inverse, and then we used QR and Svd to get the same solution. But that was an analytical solution. For nonlinear least squares, the problem is we are saying here f can be anything. In a neural network, it's like a composite function. It will be a complex function with lots of nonlinearities. Or let's say I have some function like sine of cos of x by tan of log of x. I don't even know if that makes sense. But the question is, the problem that we're trying to deal here is, if you have an incredibly complex function which is not linear in nature, can we still minimize it? That is the question. So we use numerical methods. Analytical methods, I mean, if you go deep into math, there could be some they're either time consuming or a bit specific to the question that you give. So like all in all, there are dedicated books to numerical solutions, numerical optimization. So in all of the practical scenarios, we'll solve it numerically. So what you need, although even if you solve it numerically, I don't know why this came over here. Wait. Oh yeah. Okay. Yeah. Okay. No. Yeah. So you must have seen gradient descent, right? What do we do there? We take a delta x. We call it a negative of gradient. So over here, the most general algorithm, general descent method. Descent as in minimizing the function would be I would choose a descent direction, then choose some step size t, and then I would say my next better a better solution would arrive at x, which is equal to x plus t delta x. So typically you must have done deep learning and whatnot. Over there you choose t to be 0.001 and so on. But there are nice approaches if you take applied optimization next semester or next to next semester. I do not know to which extent Java Hustle covers, but in optimization courses you will see that even for t you can arrive at a good solution for t. Solution is in good value for t. Okay, so this is the most general descent method. Any general descent method follows this. Our objective would be to find delta x. Whatever be our algorithm, we are always worried about what delta x is. Delta x could get extremely complicated as well. So if we know delta x, we'll just do t delta x and add it to x. That will give my next update, which will be slightly better than the previous one. And we have to do it iteratively until some stopping criterion is satisfied. because we are doing it numerically, we'll have to do it iteratively. It is a iterative enumeration. Okay, and since we are dealing with nonlinear functions here, we would also need good initialization. Now, this might sound very out of reach, but in most situations we do have good initialization. You in MR, let's say assignments, you will see that. Or let me give you an example. Let's say you want to do bundle adjustment. We'll revisit whatever I'm saying right now tomorrow. But let's say you can initialize using triangulation. You can initialize the world points using triangulation and then start your bundle adjustment optimization. So you do in computational SLAM methods, you do have a good initialization always. You always want to optimize on that initialization. Let's say on SLAM, you have a post graph. That also you have some initialization. You know where your robot is approximately using your sensors. It's not like using your sensors or whatever your measurement model. And from there, you want to ask what will be how will I reach a minima of my loss function? How will I find a better model? And we also assume f is locally linear. Okay. So yeah. Now
What
you must have.
linear mean?
So like since we are doing iterative minimization, you start at, let's say, x naught, and then you do this update step and then come to x1. So when you're doing this update step, when you are at x naught, at that particular region, you assume that your function is affine. I mean, locally that assumption is good enough. Even if your whole function could be extremely complicated, you can assume that in the immediate neighborhood, it is a linear function. We have to make this assumption, and it is a good enough assumption if we want to use these methods. Okay, so given these assumptions, the second and third are the assumptions. Now you have seen in gradient descent, it's one of the most common methods that we use. Over there, we say you have your gradient is in the direction of increase of a function. So I take negative of a gradient as I want to minimize my function, and that will take me into the direction of the decrease of my function. That is what we used to say always. But the thing is, that's not the only case. What criterion it has to satisfy is this, whatever you're seeing here. The search direction in any descent method must satisfy this particular condition. This is gradient of f at a particular iterative step multiplied by your delta x, the step that you're taking should be less than 0. Now what this like geometrically means is you want to make an accurate angle with the negative gradient. So as long as you make an accurate angle with the negative gradient, you will go in descent direction as long as this condition is satisfied. Now the best way to do it would be argumentative. That's why we have lots of methods. So what does acute angle with negative gradient mean? Let us see. Okay. Acute angle with negative gradient. So you have some function like this. You have this function, and we want to find in which direction the gradient would be. The gradient would be in the direction of increase of a function. So it will be something like this in this direction. Now we are looking at this point. This is xk point. Now over here, what does it say? It should make an acute angle with negative gradient. What is negative of a gradient? And remember that we want to minimize the function. We want to move in this direction. We want to sort of end up here. Negative of a gradient would be this. And what is forming an acute angle with this? It is anywhere from here to here. Here it's 90. Anywhere within that bounds, it is acute angle, right? So as long as my delta x is forming an acute angle, it's lying anywhere here, here, or here. So this in this direction would typically be your gradient descent. But as long as it is satisfying any direction which is forming acute angle with my negative of the gradient, that is fine with me. That is all I say. Fine with me as in, if I take such a delta x, it will definitely go in descent method, in descent direction. So in descent direction as in the minimization direction. So keep this at the back of your mind. It need not always be just a negative of gradient. You also have things like coordinate descent method. You kind of take longer step along one coordinate. So yeah. So we'll come back to this again in a short while, this table. But that is like the summary of what we are about to cover. Okay. Yeah. So let us define our what we're trying to minimize again. Gradient descent we have already gone through. This is our function which we want to minimize, and I take negative of that. Okay, can someone tell me what's the most simplest case you can think of for which this so the most simplest case for delta x that you can think of for which this condition holds true? So that would be the case of gradient descent. When you choose delta x to be minus of gradient of f, this would end up being minus of gradient minus of gradient square of f, which is less than 0, which is always less than 0. Yeah, so here, let's not get confused by looking at this. We'll come back to this. This is not actually let's just look at this particular equation. Delta x is equal to minus gradient of capital F. Over here also think of it as capital F. The difference between capital F and small f is that for the sake of clarity, I'll call capital F as minimization function and small f as your original function. What your original function was, what is given was because it's convenient, I'm taking the least square of it and I'm getting ending up with this capital F function. I'll call capital F minimization function and small f your, let's say, original function. So if you substitute this here, this will always end up being negative, minus of gradient square. So that's like the most natural choice. Yeah, is that fine? It's basically minus of, let's say if this is the reason like it might look intimidating is because there's too many, superscripts and whatnot. But basically it's minus of a square or b square or whatever. It's always less than 0. And it's a transpose a, so it will be, here it is gradient of f transpose into gradient of f, negative of that. So it will be norm of that, which is norm is always positive, or norm square. So that will always be positive, but you have negative sign outside, so it will always be less than 0. So that is the most natural choice that you can think of, the gradient descent. So that will be your one of the choices for delta x. Okay. Now do not get confused by looking at this table. We will come back to that later. Right now, look at capital F. Only look at capital F. The time will come when we have to look at small f. Minimization function, as I'm calling it. Okay. Now, Newton method. Let us move on to the more complex method, Newton method. So Newton method, so this is called the Newton step. Let us define it this way. We'll see why it will be the case, or at least get some intuition on it. Delta x, your step would be equal to inverse, this is Hessian, which will later represent by h, into gradient, minus of Hessian inverse into gradient. Now, so that is the definition. How do we arrive at that? Wait, look.
Oh, one quick question.
Yeah.
Hessian of f of x to the power -1 means after you calculate the second derivative, you're inverting the matrix, is it?
Yes. You're inverting the Hessian matrix.
Inverse, right. Oh,
Yeah.
okay.
Yeah.
Thank you.
Yeah. Okay. Now, since we have assumed it is locally linear, f, okay, small f, your original function, since we have assumed it to be locally linear, your capital F would be a quadratic function at that particular instant. I mean, it's not like locally it will be a quadratic function. That's what you could say. So if it's locally a quadratic function, I'm expanding this out. I'm taking a Taylor series expansion, and this is sort of my, like, if I take Taylor series expansion second order, I'll get this. Now, as it is locally quadratic, I want to take a derivative of it and then equate that to 0 in order to reach my minima. So intuitive way of looking at it would be, let's say your function is something like this, and the quadratic approximation is this. What you would do is you take a second order approximation and then take its derivative. You'll come from here to directly end up here. So that's sort of the intuition. You approximate it to a quadratic function, second order approximation, and you reach that minima in like one step. To kind of look at how we arrived at this, you can take a derivative of this equation. When you take a derivative, what would you get? Over here, you'll be left with gradient of capital F of x is equal to, or let's say plus, this would become Hessian into v. Hessian into v. So you have gradient of f of x plus Hessian into v. Take it to the other side, you get minus, and take Hessian to the other side, you get minus of Hessian into gradient is equal to your step that you want to take. Or v or delta x, here one and the same. Okay.
Can you
Okay,
repeat?
we also,
I got lost.
okay, all right. So we said we are making, since we are assumed our small f, okay, again, this image I took from that book. So like f over here, small f refers to capital F. Sorry for the confusion, but whenever I'm referring to small f, I'll call it original function. But over here, it's actually supposed to be capital F. Outside of this image, everywhere, I think it's pretty clear. I've changed it everywhere. Only in this image, whereas if small f is written, it's meant to be capital F. Okay, so what I'm saying here is, since f is locally linear, my capital F, since my original function I assumed it to be locally linear, my capital F is this thing, small f transpose into F, which will be a quadratic function. So since I assumed it to be locally linear, or my let's say minimization function to be quadratic, I'll end up getting this Hessian as positive. Hessian as positive. So I'm doing a second order approximation at a particular point, and I'm finding out it's Hessian. Hessian, as long as it is positive and it's a convex problem, I can take a first order derivative and equate it to 0, and I'll get the step that I need to take. But this is locally, as in this will only give me delta x. V is same as delta x. So you take derivative of this with let's say v or delta x over here. This gradient of capital F would be, I mean, you are taking derivative of this with respect to v, so v will disappear. And over here, when you take a derivative of v, if I didn't mention yet, I have mentioned, like, if matrix calculus is confusing for you, go to this link. I have embedded a PDF there. Yeah, and over here you will end up with like gradient square f of x into 2 into v. 2 will get cancelled by 1 by 2, so we'll end up with Hessian into v. This is second order approximation. So this is Hessian, not gradient square. This is Hessian. So yeah. So when you take a derivative, you'll get Hessian into v is equal to negative of this gradient, and you take Hessian to the other side, you end up get and that will become inverse. So it will end up being this minus of Hessian inverse into gradient of f. So this might be too much to take. I mean, I'm covering like things from a lot of books, a lot of lectures, a lot of courses in one lecture for the sake of SLAM. If it's a bit confusing, go ahead and look back. I have included all the resources. So yeah. Okay. So you can also check this particular condition that I was saying previously. It has to satisfy. For this choice of delta x, does it satisfy this condition? You can substitute delta x as this and check for yourself later on. I have included it here. It'll end up satisfying that, so I can happily travel in that particular direction. So this is again same as, I'm just using different symbols. I'm just using different symbols here. Over here, whatever this thing was, I'm representing it with H or Hessian in other words, and this I'm representing it with Jacobian, the gradient as Jacobian. So this is for any general function, our minimization function. That is what I'm representing in subscript here. So this is what we ended up at. Hessian of this minimization function into delta x is equal to minus of Jacobian of f. Jacobian of f. Jacobian of capital F is not the same as Jacobian of small f. We will take a quick look at what is the relation. Okay, so here to look at that, we can take a quick look at gradient descent. Over here, we understood that delta x is simply negative of gradient of capital F, but gradient of this capital F is nothing but u into v, u dash into v plus v dash into u. What is u dash? F of x, gradient of that is Jacobian. Gradient of f is Jacobian into f plus f into Jacobian. Now both of them are like one and the same. Like it's like a into b plus b into a. So you'll end up with 2. That's why half gets cancelled, and you'll end up with this, whatever you see in this equation. UV rule, basically UV rule, u dash v plus v dash u, and both terms are one and the same, so 2 gets cancelled. So J transpose into f of x. So that is the relation between your Jacobian of capital F and Jacobian of small f. Jacobian of capital F, and here, if I'm not including the subscript, that means it's small f. Wherever I'm not including the subscript, if it's small f. If I'm explicitly stating it, then it's capital F. So from here, I hope it's clear. Your Jacobian. So this gradient is nothing but minus of I hope that's clear. Whatever, I don't think you have transpose here. Yeah, this and this are one and the same. So it's like j into f of x plus f of x into j, and both are the same terms. So 2 gets cancelled. You get this j transpose f of x. Sorry. So Jacobian of capital F is equal to Jacobian of small f into f of x. I hope that is clear. So similarly, if you understand that, you can take derivative of this thing again. So what is Hessian? Hessian of capital F would be a derivative of Jacobian of capital F. Right. So, but we just saw that Jacobian of capital F is nothing but j of f, Jacobian of small f into f of x. So Hessian of something would be derivative of Jacobian. Jacobian of something would be like derivative of the original function. Like derivative of my function is Hessian. So here derivative of Jacobian would give me Hessian. We just told Jacobian of capital F is equal to Jacobian of small f into f of x. So if you take a derivative here, you'll end up with let's say you're doing u v dash plus v u dash, u v dash, u will remain the same, v dash, f of x derivative would be Jacobian, so it will be j transpose j plus derivative of first term into f of x. Derivative of Jacobian is Hessian of f of small f. So I think you can, if you put it on paper, if it's sounding confusing because f and capital F, whatever, if you put it on paper, you should be able to understand what I'm saying. So you'll end up with j transpose j plus Hessian transpose f if you're taking a derivative of this equation. But this derivative of this equation is nothing but derivative of a Jacobian of capital F. That is nothing but Hessian of capital F. So j transpose j plus Hessian into f of x. So that is what we got here. Hessian into f of x plus j transpose j. And Jacobian of capital F is jf into f of x. That is what we have been looking at here. J of capital F is equal to, this is gradient descent, this is also gradient descent. J of f is equal to j small f transpose into f of x. That is all we are saying here. Okay. Right. So if that, like, put pen on paper, if algebra is confusing anywhere, there's nothing much I can visually explain about the algebra. Okay. So Gauss-Newton says instead of taking this Hessian is like computationally it's very expensive. I'll just approximate Hessian as Jacobian transpose Jacobian. That is a good enough approximation. So that is one way you can look at it. H of f, you can h of capital F, you can write it as j transpose j and take it to the other side, and that's it. That's all your Gauss-Newton is. Another way would be to write in like linearize small f. One thing is, like, in standard textbooks you'll see they just say capital H I can approximate it as Jacobian transpose J, Jacobian transpose into Jacobian. But over here, you can interpret it in some other way also. We are just writing. Till now we have only dealt in capital F with capital F. Only we have never expanded f of x as such. We have only compared between Hessian of capital F and Jacobian of small f and Hessian of small f. But over here we're expanding the small f function. F of x plus j Jacobian into delta x is my first order Taylor series approximation of f of x. F of x plus Jacobian delta x, first order Taylor series expansion. I multiply these two, expand it out. You end up getting this equation, f of x transpose, f of x into j delta x. This is the second term, j delta x. You have a transpose here, so be careful. Delta x transpose j delta x. Okay, and this is f of x transpose f of x is same as capital F of x. And this is an equation in terms of delta x. Like, I mean, we want to take a derivative. Delta x is kind of my variable here. I'm at an iterate x, or usually it's xk, x subscript k. And my variable is delta x. I want to find in which direction I want to move. So I take a derivative and then equate it to 0. And then I end up with, so as delta x is my only variable here, f of x transpose j plus j transpose j into delta x is equal to 0. Take it to the other side, you end up with this equation. Okay, so that is Gauss-Newton. I know this is like too many equations here. Give me 1 second. Okay, I know there's too many equations here, but like you can go back and put pen on paper. But this is like, you know, if I have attended this lecture, this would probably save maybe 1-2 months of my time. So this is pretty helpful stuff. It's just that there's a lot to take. That's why you might feel that you're not understanding much or whatever. But like, take your time and spend time on it. It's very important. All of these are very useful for robotics or computation applications. Okay. LM is what we used for bundle adjustment, if you remember. LM is like a combination of gradient descent and Gauss-Newton. So in Gauss-Newton, we got j transpose j delta x is equal to minus j transpose f of x. And in gradient descent, you remember, I don't think I need to show you. Delta x is equal to minus j transpose f of x. It was actually Jacobian of capital F, but Jacobian of capital F is same as Jacobian of small f into f of x. So that's what we write here. If you block this term, you will get gradient descent. If you block this term, you will get Gauss-Newton. Combination of both is S11 marker with additional parameter lambda. Okay, over here we say in LM, if let's say you have updated from the last step, you have taken a small step and you have moved in some direction, and you observe that your error function became worse. Okay, let's say your error function improved. There was a reduction in error. Then what you do is you reduce your lambda. You reduce your lambda and give more weightage to automatically, which gives more weightage to j transpose j or Gauss-Newton. So in other words, if you're getting more confident about that you're going in the right direction, do one thing. Instead of taking small steps, approximate the curve, do a quadratic approximation and take one step, go from here to here in one step instead of going incrementally. That is if error is improving. So that will like converge faster. It will save your time and it will converge faster. However, if there's an increase in error, if there's an increase in error, what you do is you increase the weightage for your gradient descent. You increase your lambda value. In other words, you are kind of increasing the stochasticity of your particular update equation. So it is more bound to escape local minima, or like if it's not going in the right direction, gradient descent it's kind of more stochastic in nature. So it's more likely to escape a local minima. So that's what you do. If you have increase in error, you give more weightage to gradient descent. So this is the summary of the methods that you've seen till now. If you need a small break, I think it's 4:15. This will probably take, again, equations only. Maybe I won't go. I'll finish this off. And then maybe you can take a break. For this part, you can again, like the math is pretty clear written here. Like you can even look at it later. Okay. So nonlinear weighted least squares is a useful problem for us in robotics. You'll see tomorrow, SLAM backend. We start from here and we end up with this equation, and tomorrow we will start directly from this equation. It's important to understand this. So usually we always have norms on, let's say, L2 norm or L1 norm or L infinity norm. That always used to be some integer number here, and you used to take the norm and minimize. But you can also define norm on a vector space. So this is kind of a bit abstract algebra. I'm also not an expert on that, but this sort of norm spaces, like it falls in this category, green category that you see here, norm vector spaces, and inner product spaces that you see usually A transpose B, that is a subset of norm vector spaces. There, if you go more abstract into the math, linear algebra, there are things like metric spaces, topological spaces, and whatnot. So this, for the sake of our SLAM formulation, all you need to understand is, when I write norm on a vector space or on a matrix sigma here, in other words, it's nothing but this. So this norm on vector space on this matrix sigma is equal to F transpose sigma inverse F. What was it normally? If it was norm 2, it was simply F transpose F. So in other words, it is like just saying I want to give more weightage to some of my, let's say in one direction, I want to give more weightage to that loss. I want to minimize that loss more. And in other direction, I want to do it less. So if it was equal in all the directions, sigma will be identity matrix, and it will end up being F transpose F, which is same as your linear, it's same as your normal least squares, just taking norm square. But over here, you want to minimize it differently in different directions, so you have sigma inverse. Okay. So for the sake of this lecture, that's all you need to know. Even for understanding SLAM, F transpose sigma into F is what, like, you write sigma inverse as omega. In SLAM, I'm slightly getting confused here. One of it is called covariance matrix. One is omega. I don't know. Tomorrow, Udit will repeat that again. What is omega called? What is sigma called? Okay. So again, over here too, whatever we did during Gauss-Newton algorithm derivation, we will use a similar derivation for this. What did we do above? We just expanded out f of x. We did a linear approximation, first order approximation using Taylor expansion. Over here, you'll just end up with an extra sigma, extra omega. So you are approximating f of x again, first order approximation. Expand it out, and then take derivative with respect to delta x, and you end up with an additional sigma here. You can put pen on paper again and then see for yourself why we end up with j transpose sigma, sorry, j transpose omega j delta x minus j transpose omega transpose f of x. You're looking at so many equations, it's making me dizzy. But yeah, all of this, like, we'll start from right here in tomorrow's lecture. And the LM equivalent of this would be plus lambda I. This would be Gauss-Newton. So for it to be exactly Gauss-Newton, substitute omega as identity matrix, and then you will end up with same as Gauss-Newton. Over here you are adding lambda I. Okay, so that is the math behind given an optimization problem as complex. This is as complex as you can get. I think, like, probably, I don't know, if you are very into optimization, maybe you might go beyond it. But most of the scenarios, even if you're working in SLAM backends, which is very mathematically rigorous, this is like the maximum math you will usually use. If you're in deep learning, you won't even go through, like, you won't even need like 10% of this anyway. So yeah, it's good that practical sessions are being taken on deep learning, but at the same time, these are also very important. Okay, so tomorrow's will start from here. Tomorrow's postgraph optimization, the SLAM backend, will start right from this equation. So if it's not clear, again, I can't help stressing on the fact that you have to put pen on paper, and then we'll start from here, and we'll see how this will help us optimize our postgraph. Postgraph is basically you have a set of, okay, I don't, like, let's define that tomorrow by 2. Like, there's no, yeah. You'll see that that's a direct application on SLAM backend. Okay, so you can take like 5 minutes break now. I'll start at 4:25. Udit will teach for like maybe 20 minutes. I'll teach for 20 minutes. I'll try to keep this short, 15-20 minutes, and then yeah, we'll disperse. Okay, you can take like I don't know, 3-4 minutes break. If you are interested, you can go through this page. I have shared the whole link with you, but let me share again. If someone is taking a break, you can for like 1 or 2 more minutes. But I want to revisit one concept over here. If it's not clear, keep asking me. I think, what is it? Yeah. Okay. Yeah. I am audible, right? Am I audible?
Yeah.
Okay. Cool. Let's revisit that. When I was explaining Gauss-Newton, actually Gauss-Newton forms the basis of other methods too. Let's say, I mean, your Gauss method, not Gauss. What is it called? Newton method. Yeah, your Newton method forms the basis of Gauss, Newton, and LM. So let us revisit Newton's method again. Again, it won't take too much time. Don't worry. But I hope it should be crystal clear to you. If not, keep asking me to repeat. So in the linear least squares, we have taken a square of this and taken a square of the norm and expanded it out and took a first derivative and ended up with this equation which we call the pseudo inverse. Okay. Now Gauss-Newton, the way I have tried to explain, is also more or less the same thing. So sorry, I meant Newton's method. Yeah. So under the assumption that small f is locally linear, your capital F would be a quadratic function. You multiply two affine functions, you end up with a quadratic function. But in the previous case, when in the previous case, the one which we just saw, linear least squares, ax minus b was our linear equation, and we had the values of a and b. A matrix and b matrix were defined beforehand. That was the problem statement. The question was, if a is given and b is given, what for what value of b will I able to minimize this ax minus b, norm of ax minus b. But over here we do not have any such things. We don't have ax. We just only know what the original function is. It could be as complicated as let's say neural network composite function. It could be f of 100 times. We have lots of non-linearities. All we know is that function, and we also know the current estimate. So these 2 points, that's why they're very important. Needs good initialization and f is locally linear. Both of these we are using in Newton's method. Since f is locally linear, your capital F of x is quadratic. If capital F of x is quadratic, I mean, capital F of x is not just quadratic. It's a special quadratic function where it's a product of two linear functions. So whenever it's a product of two linear functions, you end up with this sort of a thing: x transpose a transpose ax, and a transpose a will be a positive definite. So a transpose a, whatever it is, like m transpose m, whatever m is, it is always positive definite. It is always positive definite. So that is the thing. That is the case below also. It's a product of two linear functions. So it's a special case of a quadratic function, and the term that you get, the constant that you get with your quadratic term x transpose x is definitely bound to be positive definite. I mean, if you take a double derivative of this, you end up with a positive definite matrix. So if you get a positive definite matrix, give me once again. The second order condition of convexity says if second derivative is always positive definite, then it is a convex problem and I can just take the first derivative and equate it to 0. I hope that is clear. And if that is clear, in the below case also, it is essentially the same thing. But the only difference is we did not have A and B beforehand. So instead of taking A and B, because we do not know, we take a second order approximation of A and B. See, what am I saying? Second order approximation of capital F, and at a particular, and if we do not know anything about X, we cannot take approximation, right? What does it mean to take an approximation without knowing the initial point? Since we have a good initialization, x naught, small x is x naught here. At that particular x naught, I will take my approximation. If I take my approximation, if you recollect what Taylor series is, it will be, even if it's a extremely complex function, I can either approximate it as a linear function by taking first order term. I can approximate it as a quadratic equation by taking second order term. And the unknowns over here would be only the delta x's or v's. And the knowns, because you know the initial point and or the point where you are, x naught, and you know the function, the huge that your crazy ass function, you can substitute f of x, and this will be a constant. Gradient of f of x, this will be another constant into v, which is your variable, and this will essentially the same as your previous linear equation, locally speaking. And whatever you end up with, this will always be positive because it's a product of two linear functions. Two linear functions, A transpose A is always positive. So then, see, applying same logic, we say it's a convex optimization function. So I take first derivative and equate it to 0. If you take first derivative and equate it to 0 and find the value of v or delta x, you'll end up with this. We have seen that. Is that clear? Is Newton's method clear now? If there was confusion before. If Mithun or Udit want to add something, you can. Can someone give me yes or no? If there's something unclear, you can, like, if it's specific, if you didn't understand the whole thing, maybe you'll have to revisit that again at your own leisure. But if there's something specific, you can ask.
I have one question towards non-linear weighted LS.
Okay.
So in the derivation, like I got until the last line, but and then we added lambda I in the LHS. How did we do that? Yeah, from that to the next box.
It is just a LM variant. So
Okay.
yeah, previously that's what we did for LM, right? Wherever you ended up at in Gauss-Newton, J transpose G, we just started lambda I and called it LM algorithm. That is what we're doing here also, just adding that gradient descent factor.
Okay, I thought it was part of the derivation, so I got confused.
No, that's okay.
Oh.
Any other questions? Okay, then if you understood Newton's method, if if you understood this this solution, basically delta x is equal to minus of Hessian inverse into Jacobian. If that much is understood, then you can, it's just matrix algebra. Like after that, that was on Hessian was on my minimization function. If I want to write in terms of Hessian in terms of your original function, you'll get this. You just have to put pen on paper, take a derivative, you'll get this. And then Gauss-Newton would be you're approximating Hessian to J transpose J, you'll get Gauss-Newton. And then Leavenworth-Marquardt is a combination of gradient descent and Gauss-Newton. That's all you have to know. And for non-weighted least squares, you have this additional thing here. By taking that also into account, you minimize. Okay, I'm moving on then. If you do not have any doubts, you can always, the best way to ask doubts after the lecture would be to comment on this page rather than reaching me on WhatsApp. WhatsApp or Teams is also fine, but if you answer here, if you ask question here, then I'll be quick to respond, and also it'll be easy to refer for me also. Okay, let me quickly cover ICP. This will hopefully I won't go too much deep into the math here. We have saw enough math for today, I guess. Okay, so yeah. Okay, we'll see the big picture again tomorrow. What's the point of repeating again and again? Basically, the objective of this part of the lecture is if you know the 3D correspondences. In the previous cases, we have seen if you know 2D correspondences, what sort of information can you extract? You can compute F given enough correspondences, and then you can decompose E into RT. This is one way of doing it. You can, using RT, you can also use triangulation to get your world point. You have also seen PNP where you have 2D, 3D correspondences. You can estimate your pose. Now we are looking at 3D correspondences. If you have your 3D correspondences, let us say look at like this one point cloud, green point cloud, and the black point cloud are separated by some rigid body transformation. You can think of point cloud as a set of points. They're separated by rigid body transformation. Basically, you're rotating them by a certain rotation and then translating them by certain translation, whatever way to put it. Anyway, so a practical example would be you're traveling in a car. Let's say you have you're looking at a building which is 10 meters away from you, and you have moved 5 meters. Now it will look to you that the building has come closer, although the building was a static thing right there. It will seem to you like the building has come closer to you by 5 meters. So if you're holding a camera and you are capturing that point cloud at your point A, and then you moved 5 meters and you took another point cloud set of points, 3D points at point B, you are moved by 5 meters. Now if you found out how much in your camera or in your eyes, how much your building has moved, if you found that out, then you'll obviously know how much you have moved. That is the whole, that's how we can estimate your pose. By finding out how much that object has moved. Object has moved by 5 meters. That means since the object is static, that means you must have moved by 5 meters. The camera must have moved by 5 meters. That is all there is in this lecture. Like you want to find out that transformation. Using that transformation, you can find out where you are going. Okay, so let us consider 2 point sets. So although both of them correspond to the same thing, since they are separated by a rigid body transformation, we can think of them as 2 point sets, and x1 2 point sets. Like for the sake of discussion, let's say they have equal number of points, and x1 is corresponding to p1, x2 is corresponding to p2. As in corresponding means x1, let's say x1 is your like first window on the building, the tip of first window, And P1 is also that same point, but it's just translated and rotated by some amount in your frame. Now you want, as you have been saying, both of them are separated by just a rigid body transformation. So as has been covered in transformations lecture, if you apply a rotation on that point and subtract it by some and move it by some distance, translate it, then it has to, if they're corresponding to the same point and both the point sets are separated by rigid body transformation, then for the same RT, for a fixed RT, both of those have to completely overlap, because both of them are exactly the same thing. Both of them are windows. It's just that they are in different frames. You can think of them as they're just moved by a certain distance. So this is the error function that we want to minimize. So the good thing about ICP, as in you do have, we'll see. Okay, so the good thing about ICP is that if you have corresponding points, if you know, okay, this particular point corresponds to this particular point, and you have a few sets of correspondences, then you can find out the correct R and T. When I say R and T, I mean rotation and translation in closed form. There's no ambiguity here. There's just one analytical solution. You don't need any iterations. If you know the correspondences, you can get it in one shot. You can get the RT in one shot. So the method that you employ for finding out your RT in the case of known correspondences is, firstly, you find center of mass. I mean, intuitively, you can think of it as, the reason you want to find center of mass is because, let's say you're at a point A and you have measured some, let's say you're looking at a circular object, and the edge of, like, let's say there's a paint at the edge of that circular object, and from your first frame it is like 5 meters ahead of you, 5 meters ahead, like let's say 5 in x direction, 3 in y direction, and you have moved by like translated by some distance, and in your frame it is something like 2,1. But what does it mean? You defining it in your frame doesn't make much sense. So you try to, since they are both corresponding to the same object, you kind of want to define it in its own frame, as in with respect to its center of mass. So you find out the center of mass of first point load and second point load, and then subtract each point from that centroid. So if you do that, then it's more like that paint that I was talking about in both the frames would have a similar representation when compared to my original X size. This capital X dash, whatever, or a small x dash, I've come up with the new way of measuring it. It would make more sense. They would have similar representation in that space. Okay, so we're just going to discuss theorem here. Even in like Wolfram Baumgart's lecture, this is what they to cover. I think it can get quite mathematically rigorous. If you want to go into the derivation, feel free to, and like I've added here, if you want to contribute here, you can. But for this particular lecture, we will not be covering it. So you take that centroids and multiply with each other, and define a sort of a loss function sort of a thing as summation of all of those. So you have distance. This is basically distance of a point I from my centroid, and you have distance of a point I from my second point load centroid. Multiply that and keep adding. That is my W. You apply a singular value decomposition, and then RT are given in closed form by this set of equation. R will be U into V transpose, and once you know R, you can find out T. This is more intuitive, right? Getting T from R. Yeah, it's just like once you have corrected for rotation, once you've corrected for rotation, you can just subtract the centroids between those 2 point clouds to know. Basically, they are facing the same orientation. So I can just subtract those two centroids to get how much they're translated by. And the corresponding error function is given by this. I'm not going too much detail into this. Okay. But what you need to remember, if you have known correspondences, it's a closed form solution. The math might be a bit like tricky, but it's a closed form solution, and it's not common that you see closed form solutions appearing in your SLAM or anywhere in general. Okay. Now, what if you do not know if you have unknown correspondences? That is what happens in most cases, right? So it is generally impossible to determine relative RT in one step. You have to apply some iterative nodes, iterative methods, but it is assured to converge if starting points are close enough. Points. Like usually in most of like traditionally, you just take the most traditional method of taking your corresponding point would be to take the closest point to your current point. Let's say I'm looking at this point here. Whatever is closest to me in my second point cloud, I'll take that as my corresponding point. I have some point here. I'll see which is closest in my second point cloud. That will be my corresponding point. That is one way of finding the corresponding point. Other way is normal shooting. You shoot a normal, and wherever it intersects this point cloud or this curve, that is my corresponding point. And you have more methods, closest compatible point prediction based. There's a lot of work done on ICP. Especially, I mean, if you have something like the moment you have 3D data, you can apply ICP and find out where you're moving. So it's an iterative. That's where it gets its name from, iterative point cloud. So you determine corresponding points using a method like this, and then compute RT via SVD. This particular step is a closed form solution. I mean, from starting from your initialization, if you apply the method that we discussed above, it is assured to go into it is assured to give a better RT. I mean, you're going closer to your solution. And then you apply RT, get the point clouds closer. They are still not completely registered, but they come closer, and they are like more corresponding now. Compute error, if its error is less than a particular threshold, like if it's greater than a particular threshold, repeat these steps, and then if else you can stop. Yeah, so there are like methods which use non-linear optimizations also. For a lot of these things, there are much complex implementation. For the sake of these lectures, we'll obviously be dealing with the bare minimum. If you are interested, you can go ahead and look. So yeah, I just included some open source implementation for you guys to play around with. Lip point matches, I've used this about like a year back. It's very good. This is what I like the most. It's by ETH Zurich. You can also take a look at Open3D. Open3D has a lot of more functionalities. Coherent point drift. These are just for you to explore. I think that's pretty much it. from ICP. ICP, I hope you have understood it at a, at least at a high level, what is going on. Like, our essential goal is to find RT. Okay, I think Udit can start. Udit, are you online?
Yeah, I'm online. Like, yeah. Should I start right now, or students want to take a break? Like,
I think we have given them one break, so it's 4:50 already. We will only be taking 20 minutes anyway, right?
yeah. Max 20 minutes.
Okay. Then you can go ahead.
Okay. Okay, so I will, like, yeah, it will be like 15-20 minutes, so I can start right now. Okay.
Yeah, go on.
My screen is visible now.
Yeah, Udit.
Okay. Okay, so now we will cover the loop closure part in SLAM. Tomorrow we will be seeing the complete picture of what is SLAM, but right now we are going to cover the first part of the front end of SLAM, which is loop closure. And here I'm going to discuss like bag of visual words approach. Okay, so first, what is loop closure? So like I will start with an example. So on the left side, you can see there is a ground truth trajectory. Like a robot start from 0, 0, and it went through a circle. It went through a square and returns to its original position. But and
Udit, I think, are you guys able to read, is this how it is when I share my screen? I'm not able to read what is written on the screen. You can zoom in. Control plus, you can zoom in.
okay, 1 second.
Like, increase the page size.
Okay.
That's one downside of using Notion here.
Is it visible now?
Yeah. Wow, you can actually, there's one feature where you can zoom in the screen from within Teams. Like select, click on your whatever you're seeing, and then click on Control plus. It is zooming in your screen. Nice. Anyway, go on.
It is visible now? Yeah, okay. Okay, so here's the robot trajectory. So this trajectory is generated using GPS. So we will call this a ground trajectory or some external motion capture sensor, which is seeing what is our ground trajectory. But in reality, what we observe from the robot, like if we have some sensor on the robot, like a camera, which we are going to use to calculate our odometry, or like a wheel odometer, then this will be the trajectory which we would get. So these are represented by blue circles. So as you can see, there is a drift. Drift might arise uh, due to slip in the wheel. So as the robot started from 0, 0, but when it again come to the same position, so it is at this position. So it is I'd say like 0, 5, but it should be 0, 0. So but we know this is not a correct ground truth trajectory, and we want to correct this. So there the loop closure things come in. Loop closure thing is basically telling our SLAM system that we have visited the same place again. Okay, and this green line show what like the output of our loop closure systems. So it is saying like this place belongs to this place. Like similarly, this things belongs to this place. Okay, so now SLAM representation. So I will just give a quick overview what is a SLAM problem. So like in SLAM problem, we have like landmarks or your maps. Landmarks can be your tables here, like if you are talking about indoor environment, and these are your landmarks. These are your unobservable random variables because like you only observe the sensor measurements. From sensor measurements, you decide the position of your landmarks. That's why I'm calling it unobservable landmarks. And this dark squares are your observable landmarks, observable random variables. So Z1, Z2, Z3 are your sensor measurements. It can be your RGB measurement or your LiDAR measurement. Uh, Again, X1, X2, X3 are unobservable random variables, and these are robot positions. And U1, U2, U3 are your wheel odometry or your control input. So you know what is the value of your control input. That's why these are observable uh, random variables. So this is a SLAM problem, and this is sort of a conditional dependency graph. So it says which variable depends on which of the previous variables. Like if you see this x2 depends on the previous pose, robot pose, which is x1, and also the input u1. Okay. And yeah, and for the SLAM problem, our main target is to calculate this probability distribution. Uh, like we want to calculate the robot poses and the map of the environment. Map of the environment is this landmarks. So we want to calculate this the probability distribution of this unobservable random variables from this observable random variables. UT and ZT are the control input and the sensor measurements respectively. So yeah, our whole SLAM problem is targeted towards finding this probability distribution. But currently, we are only looking at this loop closure thing. What is this loop closure and how we are going to uh, find it? Okay. So now, what is the bag of visual words approach? So bag of words, visual words approach is basically a problem where we are given a query image and we have a set of database images, and we want to say which are the most similar database images given corresponding to our query image. So like say this is a robot and it has this query image like taken at this particular moment, and it want to say which particular room it belongs to. Like these all rooms were in its data set, and it wants to say which particular room this current image belongs to. So that is what data association or loop closure problem is. So most of the solutions of this bag of visual words approach is taken from this uh, natural language processing community. Like if you guys have visited the archive Sanity, and if archive Sanity by Andre Karpathy, and like if you type any name of the paper, then there is one feature called show similar papers. So if you click show similar, then it will list out the most similar papers given to a query paper, like based on the unique words which appear in your paper and the database papers. So it uses one algorithm called TF-IDF, which basically looks for the uniqueness of the words in your query paper and the database paper. So that same idea is also borrowed by the computer vision community to say which image uh, correspond to the query image from the database images. Okay, so now, what is the representation of bag of visual words approach? So uh, in text, when you want to do searching over a text, it is quite clear that your words are pretty simple. Like words, you know what is words and what is dictionary. But in terms of like images, you need to define words. So here we define visual words as a 128 dimension vector. Not needed to be a 128 dimension vector, but generally if you are using a Swift feature detector, then this visual word is a 128 dimension vector. So here, let's say we have three images, and these are the words present in our dictionary. So words, as I have said, that basically they are a high dimension feature vector. Let's say it is a 128 dimension feature vector if you are using a Swift feature detector, and those words are fixed in your dictionary. Your dictionary is basically a collection of visual words. All these 128 dimension words, feature vectors, which you will use which you will use to say use to say which words are present in your image. So let's say this is your image. So what are the visual words present in our image? And let's say these are the words present in your dictionary. So let's say your dictionary only contains 4 words. So words are the uh, this cycle thing, this skin color, this part of a guitar, and this eye. So so you can see the words for this corresponding to this particular image uh, give a high bin value of this of the histogram. Like the skin word is very high, and like the value of the histogram on the y-axis is quite high, and this eye thing is pretty high. So so this will be the representation. This histogram will be the representation corresponding to this image. So this is sort of an overview, and similarly for these two images. And one more thing, so there is a pre-processing step before you do any bag of visual words. First, to create a dictionary, and once you create a dictionary, then dictionary size will be fixed, the number of words will be fixed, and uh, the order of the words in your histogram will be fixed, so that each image will have a standard. Like all the images will be on the same ground, so all images will have a standard representation. So like these things need to be fixed. The words in your dictionary, the order they appear on the x-axis in the dictionary, on the histogram should be fixed. Okay, so now let's start how we are going to get this descriptors and how we are going to build this dictionary. So let's say you have this image. This is a grayscale image. Okay, so so this is your image. So so you do some feature detection. Let's say you use Shift, then you will get key points, and corresponding to key points, Shift also gives you the descriptors. So descriptors are around that key points. So let's say you get a key point here, and you will get a descriptor here. So let's say you will get different types of descriptors. So you can take those 128 dimension descriptors and just scrap the whole image. So this is your so you see what are the words available. So let's say you apply Swift detection algorithm, and you get a 128 dimension feature vector, and you see which word is more similar to this extracted descriptor. So so you said like this key point is more similar to this red descriptor present in your dictionary, and similarly for this red point. So in this particular fashion, you built a representation of your image using the words present in your dictionary. These words are fixed, but the number of their words are defined by the image, by your given image. So once you got this representation using the predefined words in your dictionary, then you can scrap out this image. Then this particular representation is enough for us to query the images from the database. Okay, so let's say now we are going to build a histogram from this representation. So let's say so I earlier I said the order should be fixed. So let's say our order is first word will be blue, like blue descriptor. Like blue descriptor can be any descriptor. I'm just coloring it. So to say, I'm just coloring it. So it can be a 128 dimension feature vector, but let's say it should be blue. Like blue color is a representation of that feature vector. So of that particular word. So blue, red, green, yellow, and orange. So like and y-axis represent the number of times they occur. Like basically a histogram where the bin length along along the y-axis represents how many times they occur in that particular image. So this is a representation, like blue occurs 5 times, red appears 2 times, green appears 1 time, and like yellow and orange does not appear in this image. So the representation, so you can basically represent this image using this feature vector 521000. So this is this is quite good enough to represent this particular image. So it is one thing to note that like in practical cases, words will be like thousands or 10,000. It won't be a five. So your dictionary won't only contains this uh, only 5 words. So then in that case, your feature representation is unique. So it won't. So it would be unique. And also, like, this is a very compact representation. Like if you see this image, so and this is a very small vector compared to the data present in this image, so it is quite compact, and that's why we used in slam, like this is a 5-dimension feature vector corresponding to this whole image. So that's why we use this bag of words, visual words approach in slam thing, because there we want to do fast computations, because our input is coming at a very high frame rate, and we want to compare our current image to the past database images which we are also building on the fly. Okay, so like, yeah, as I said, what are the steps? Extract key points, represent the key points with the closest visual words in dictionary, and represent the occurrence of visual words in a histogram. Now we will see how we are going to build a dictionary. So you do. So in most of the cases, you don't need to build a dictionary. You can use the state-of-the-arts available dictionary like DB or OW2, like bag of visual words or library is there, so you can directly use that, and it is trained on indoor and outdoor data sets. But like, let's say if you want to do on some random data sets, or you want to build your own dictionary, so like how you will go about that? So building a dictionary is a unsupervised, like is you will build a dictionary in an unsupervised way. So we don't need any manual annotations. So okay, so basically, our dictionary defines the list of words that occur in given image, and we will build using unsupervised technique. So first of all, you will choose the descriptor. No, you will choose the feature detector. So what, whether you want to use the Swift feature detector, whether you want to use the ORV feature detector, or whether you want to use some deep learning feature detector like Superpoint. So first you will decide what is your feature detector. Once you decide what is the feature detector, then it will remain same throughout the pipeline. Uh, like the feature detector which is used to build a dictionary would be the same as during your inference time. Like the during inference time, you will use the same feature detector. You can't build a dictionary using ORB feature detector and during inference time use Superpoint feature detector. Okay, so what is how to build a dictionary? So let's say you have like images in your database, this image, like thousands, 100,000 or millions of images, and from this million image you run a feature detector. Let's say you run your Swift feature detector, and for each image, like this is one image, this blue thing is one image, this another blue thing is another image, and this so forth. You have like so many images, and this black lines correspond to a descriptor in the image. So this black thing corresponds to one descriptor in that image, second black line corresponds to second descriptor in that image, and so on. So you have this image which in turns contains the descriptors. So you have this number of images and this many descriptors. So now what we want to do is we want to get the most representative descriptors out of all the descriptors present in all the images, because like there will be some repetition and we want to avoid redundancy. So we will choose the most unique descriptors to act as a word in our dictionary. And once we build a dictionary, then we will use that dictionary in dictionary in inference time. So we will do this k-means algorithms. So first we have 128 dimension feature vectors. We will project 128. So So this is a 2D case, but generally this will be like, let's say 128 dimension feature vectors. Then you will do k-means, and after doing k-means, let's say k-means decide the set. K will decide the number of visual words you want to be in your dictionary. The centroids, the number of centroids are basically the number of visual words. Like say you want to have a dictionary of 1,000 or 10,000 words, then you will set k is equal to 1,000 or 10,000, and that thousands and or 10,000 will say what are the most prominent descriptors present in all the database images. And yeah, and those will be the words against which you will be comparing your against which you will be comparing descriptors obtained during inference time. Okay, so you use all the database images, extract descriptors into k-mean, and the centroids will be the words in your dictionary. Now, what about the inference time? So input will be the let's say you want to do this bag of visual words approach from scratch. So input will be the database, like input will be database images to build dictionary. As I earlier said, you don't need to dictionary every time. You can use the third party available dictionaries, and they are built on like much larger data sets. Like it also contains indoor data sets and outdoor data sets. But if you want to build a dictionary, then you need a database images, and you need obviously query images which you want to query, and the output will be for each query image what are the most and similar database images. So now I'm just saying how query images are converted to a histogram. Let's like earlier we saw that this contains 5 blue words. So then like as I am saying blue words, like it means visual words, and visual words is basically a descriptor. And this image does not contain any red visual word, so it will be 0. And similarly for this all the four images. Now how we are going to compare the how we are going to compare this histograms. So once you use these histograms, then I said you will get this feature vector. Like 52100 will describe this whole image, and 40100 will describe this image, and similarly these vectors will describe these images. So we are going to use this cosine similarity uh, to say whether two histograms of which are the basic representation of our image are same or not, to say whether two images are same or not. So cosine similarity will basically tell us what is the angle between those vectors. If the angles, like if the vectors are pointing in the same direction, then they are perfectly aligned. And if they are orthogonally, if they are pointing orthogonally, then they are not aligned. So that is what our cosine distance similarity measures say, like basically x transpose y divided by the norm of x and y. And but we will use this in like opposite of cosine distance, because cosine distance will give 1 when when vectors are looking at the same direction, because cos 0 is 1 and cos 90 is 0. But we want opposite of that, like if vectors are looking into the same direction, then it should give a low loss value like 0. And if it is looking at orthogonal direction, then it should give like high value. That's why we will do 1 minus cosine. So this is our this is our comparison matrix, distance, so cosine distance matrix. So now there is example. So like if you want to compare these two feature vectors, so let's say you have this histogram and this histogram. So this is basically a cost matrix. So it will say based calculating using this cosine formula. So it will say which things are similar. So if two images are similar, then remember we will get a 0 value. So all images are similar to themselves. That's why along the diagonal axis we get 0, 0, 0. And also this first and the last first and the fourth image histograms are quite similar. That's why we also get a 0 value corresponding to that. Means first image is quite similar to fourth image as well. That's why we get a 0 value along this this coordinate and this coordinate as well. But rest are not same. Like this image and this image are not same. That's why we get 1 value, and other values are quite high, like 0.98 and 1. But first and fourth are same. That's why we get a 0 value. So this is what we want from our cost matrix. Now there is also one more thing. Like uh, all words are not expressive enough. So you need to take into account the uniqueness of the words. Like if a word is occurring in every image, so it is not quite helpful to say like whether these two images are the same, because it is occurring in every image. So you want to look for the uniqueness of that particular word. So that's why that's where this TF-IDF reweighting things come. Like it gives higher weightage to unique terms. The full form of TF-IDF is term frequency and inverse document frequency. This inverse document frequency is basically giving higher weightage to unique words. So here is this formula. So basically, so instead of numbers, like how many times this particular word comes in a particular image, we will use the y-axis now will represent the value of this PID will be represented on the y-axis instead of how many times that particular word comes in that particular image. So first term is called is the frequency term. So it tells how many it tells how frequent a particular word occur in a particular image, and ni, and the second term, this log n upon ni, will say how unique is that particular word. So here I is a word and d is an image. So here we will say how unique is that particular word. So second term is the uniqueness term and first term is the frequency term. So TID is the histogram bin of word I for image D. Image is D and word is I. NID is the occurrence of word I in image D. ND is the number of word occurrences in image D. Like I will go through example to make it more clear. And like n is the number of images, total images in your database, and ni is the number of images that contain the word I. So as you can see, it is like n upon ni. So it is the total number of images, and ni is the number of images that contain that particular word I. So if a word occur a very less time, so this will be a quite high value, and if word occur in all the images, then it will be n by n. So it will be log of 1, which is 0. So yeah, as we discussed the logic earlier, like if a word is occurring in every image, it is not useful. So similarly, if you can see that if a word is occurring in every image, we will get ni is equal to capital N, which will make log 1, which is equal to 0. Okay, to make things more clear, so here is an example of that. Let's say like n is the number of images. Okay, so like these are 4 images, and this is the bin histogram which we earlier created. NID, like NID is how many times a word I occurs in image D. So this blue occurs 5 times. Blue word occurs 5 times. This red word occurs 2 times, and similarly this blue word occurs 4 times in this image. And yeah, for all this image, and ND is the total number of words. Yeah, ND is the total number of word occurrence is image D. Okay, so how many words occur in this image? So 5 plus 2 plus 1. So like total there are 8 words in this image. Here there are 6 words in this image. There are 7 words, and here there are 4 words in this image. And NI represents how many times a particular uh, means how many images contains that particular word. So blue word is in all the images. Red word is only in 3 images. It is not in this images. 4 occurs in every image, 1 occurs in only this image, and orange occur only in this image. So as you can see, this word orange and yellow are quite unique. So these are quite useful. So, but for like blue thing occur in all the images, so it is not that much helpful because uh, because it is not that much helpful because if you have like another query images, so it is a high chance that it will also contains that blue word, and you can't say which. So it is more similar to which images because all the images contains blue word. But if you have a query image which contains a yellow word, then you can immediately say that there is only one image in your database which contains a yellow word. So there is a high chance that uh, that image is from this, that image belongs to this. That image is more similar to this second image. And here are the TF-IDF values. So using our formula, this we can calculate we can calculate values. So let's go through only the first example. Like the denominator contains the total number of words. So total number of words in first image is 8. So denominator is 8 in all this thing. And then it says how many times this blue word occurs. So it occurs 5 times. And then here you are saying total number of images. Like total number of images is 4 divided by the like the number of images that blue word occurs. So it occurs in again all the images. So it is 4. So this is 0. So TID value is 0. So yeah, so it is 0 for this value. So similarly, you can calculate. So this will be the length of the bin in our histogram. So this length is 0. So uh, we are giving no importance to this word occurring is in this particular image. So yeah, so it is done for all like all the words for all the images. So you will get this matrix of 5, yeah, of 5 cross 5, a square matrix you will get. And yeah, and after reweighting histograms based on, not based on the occurrence of words, but based on the using TF IDF into account, we will see these are the reweighted histograms. So yeah, so we gave 0 importance to blue thing in all the histograms because there will be a term 4 by 4, a log 4 by 4 in all the things. And yeah, so these are the histograms corresponding to uh, corresponding to all the images. And from this histogram we can see the first image and the second image are almost the same. So we can say that they belongs to the same region. But as also you can see in the feature, like in the bag of visual words, also like all the visual words which are present in this image are also present in this image. Like it contains red visual word, blue visual word, green visual word. So like first and the fourth image are same, which we obtained also from the histogram of TF-IDF reweighted histograms, but we did not obtain this using this normal histogram, which from this normal histogram we can't say this first and fourth images are similar. But after doing TF-IDF reweighting, we can say that the first and the fourth histograms are similar, the same. So okay, so this is what TF-IDF and how we are going to build a dictionary. So now bag of visual words approach is uh, like is ended. Now this is the last topic. So I will just take like 1-2 minutes. So now we get the image pairs from bag of visual words, which says which two words are which two image pairs are the same. Like let's say your robot is moving in a indoor indoor environment, in an indoor lab type of environment, and you have database images. And if a robot sees some place again which it has already revisited, then your bag of visual world approach will give you the database image which is more similar to your current image. So once you get the database image similar to your current image, that will be your loop closure thing. Because in the first place we read about bag of visual words approach to do the loop closure thing, because we want to correct the drift. That's why we read this bag of visual words approach. So once this bag of visual words say, let's say this image looks more similar to this image, then we also want to get this RNT transformation between these two images, so that we can correct the drift. If you know this, the RNT transformation between these two image pairs or these two robot locations, then you can apply this RNT transformation uh, to this shifted trajectory, so that it will overlap and hence you will correct the drift. So this bag of visual words is used to correct the drift, to propose the most similar image from the database corresponding to your current image to correct the drift. So you are going to use this ICP algorithm, which Shubodh has also earlier, like just like half an hour ago, he mentioned what is ICP. So using ICP, you are going to get the RNT transformation between the two robot locations, because your robot might be equipped with RGB and depth sensors, and you will be getting some point clouds. So you can apply this ICP algorithm to calculate the RNT estimations between these two robot locations. So here is one example, like we have worked on some projects. So this example is taken from that. So here I only use the floor floor features to like floor features as correspondences between these two images. You can use other features as well, but we are only interested in floors. So, and also like there is some irregularities in floor which we exploited. So from there we get the correspondences images. Then if we will back project that, if you project that correspondences into 3D, then you can do manual ICP. As Shubodh has mentioned, like there are two ICP variants, manual ICP and like ICP without like ICP with correspondences, where correspondences are known, or when you don't know the correspondences and you want to calculate the correspondences. So here like I use like normal surf algorithm to get the feature vectors like to match the correspondences, but there are some pre-processing involved, like we have not directly applied surf detectors on the complete image, but applied on the top view of the floor. That is irrelevant. But yeah, once you get this manual like this correspondences, then you can project those correspondences into 3D, and then you can do ICP, and the ICP output will look something like this. So yeah, the main thing is for you to say look like how the output of this ICP looks like. So you can see like this is one corridor and this is another corridor, and ICP is correctly able to match this floor regions, and it is saying, and hence you will get this RAT estimation, what is the rotation, and if the 2 point clouds are perfectly aligned, then you can say those are the RT estimates are correct, and those RT estimates you can use to correct the drift. Okay. Yeah, that's it from loop closure. Like if you have any doubts, you can ask. I don't use any feature matching the fact that's when I
Just a thought. So this will only work if there's like unique identification points at each. For example, the square thing at unique. There'll be unique identification points at each corner of the square, right? Like for example, if we put it in a corridor, like and then it goes to the left, which has another identical corridor. Won't the feature mappings get messed up because both corridors are sort of identical, but you haven't completed your loop, so won't it get messed up there? Like,
yeah. That it's a very good question, and yeah, like there's a big research field working on those things. So this problem is called visual aliasing, and like we have different type of methods working on that. So it is like good that you asked that question. So as I said, the problem is called visual aliasing. If two images if two images look similar, or if you are working on a corridor type of things where you mentioned like they are more like they are repeating scenes, and there are many techniques to tackle that thing. So from the optimization point of view, from the theoretical point of view, you can use some robust optimizers. Like Shubodh has mentioned least square optimizer, but there is something also called robust optimizers, where you will tackle the outliers. So if your front end is giving wrong image pairs, then also your back end, in your theory, in your cost function, you can design such that it will reject the outliers. Like you will design your cost function such that like it will reject the wrong outliers proposed by your front end. So that is from a back end point of view, and from the front end point of view. So corresponding particularly to this particular problem, we have not used the whole image. We have only used the floor patches, and also we were also taking the temporal information into account. So we are not so like there should be some particular sequence should match to a particular sequence. So we are not just taking a particular image and matching to a particular image. So I have not mentioned it because that is not a part of the problem, but we are also taking this temporal information into account. We were taking the top view of the floor patches, and then we were matching. But yeah, as you said, like there might be visualizing problems, so it is there. So like people go through robust optimization techniques or different type of techniques to tackle this visualizing problem. So yeah, like it is still research field and people are working, but yeah, we can tell you more about this robust optimization thing. So yeah. And yeah, any more questions? Okay, so yeah, you guys can ask questions later through like in the notions or yeah, mail. Okay. Okay, so like we will. Okay, Shubodh, do you have anything else to say, or like we should? Yeah. Okay, I think Shubodh left the conversation. So yeah, you guys can join. So like yeah, tomorrow we will be going through SLAM, like the complete mathematical point of view of the SLAM formulation, and then you can also like you can build a bigger picture how all these components are connected together tomorrow. As of now, yeah, like yeah, you guys can leave. Yeah, that's it. Thanks.